So there are some random variables that are especially important. They're common and have structure that we see again and again and can be sort of gracefully worked on mathematically. And so these are random variables that sometimes have what we call special distributions. And in this video, I want to focus on two of them, the Bernoulli and binomial distributions. So what we're going to do is we're going to look at some of these special random variables, and we're going to focus on their PMFs, their probability mass functions. So first random variable that we're going to be especially interested in is a Bernoulli random variable. We've actually seen instances of the Bernoulli random variable before. The Bernoulli random variable is the random variable that models the idea of a single coin flip. So a Bernoulli random variable has value equal to 1 with probability p and value equal to 0 with probability 1 minus p. So you can think of that as I flip a biased coin with probability of heads equal to p. If the coin comes up heads, I log a 1. If the coin comes up tails, I log a 0. So the PMF of the Bernoulli distribution, it can be written in a few ways, but I'm going to focus on one that looks a little bit funny. So the reason I'm going to do this is that I don't really want to write this in cases. So I could do this in cases, for example. The PMF is 1 if, or the PMF is p if the value of x is 1. It's 1 minus p if the value of x is 0. I could do that. But here's a slicker way, actually. The PMF is p to the x times 1 minus p raised to the 1 minus x for x in 0, 1. And you might ask, this is horrible, Phil, why did you write it that way? But let's at least check, okay, if I plug in x equals 0 here, well, this first term is going to become 1 because anything raised to the 0th power is 1. And then this is going to be a 1 here, so I'm going to get 1 minus p to the 1th power, which is simply 1 minus p, which is the right answer. 1 minus p is the value at 0. And then similarly, if I plug in x equals 1, this last term, this is going to become 0 up here. This last term is going to cancel into a 1, and I'm going to be left with simply a p. So this does indeed give the right answer, and it's helpful in a lot of contexts when we're working with these algebraically. So once we've introduced the Bernoulli distribution, the idea that we are modeling flipping a biased coin, and we can express the probability mass function in this formulaic way, let's now develop this a little further. What if I have many independent Bernoulli random variables? So suppose that I sample n independent Bernoulli random variables, which all have a success probability. That's often our standard word for p. So success probability equal to p. And I want to count the number of ones that I get. So you can think of this as counting the number of heads that we get in a sequence of coin flips. What's the probability mass function? What's the probability that, for example, I get k of these random variables equal to 1 when I do n samples? So what we're going to do here is we're going to figure this out by considering a single sequence that I'll call S with a total of k ones and a total of n minus k zeros. So you can sort of visualize S. So like S equals 0, 1, 1, 0, 1, 0, 0, 1, 1, 1. So you can think about S as just a sequence of ones and zeros, and we're assuming it has exactly k ones and exactly n minus k zeros. The probability of this sequence is, okay, let's see if we can figure out what's the probability of getting this exact sequence S. Well, in the first element here, I got a 0, so that happened with probability 1 minus p. And furthermore, I know that there were n minus k zeros, and so this 1 minus p probability event had to happen a total of n minus k times. Similarly, I know there were k heads, and each of those happened k times. So I have p to the k times 1 minus p raised to the n minus k as the probability of this single string s. So now what I need to do is I need to ask how many strings have exactly k1s and n minus k zeros. Well, guess what? I have a string. It has n bits. We can think of these as bits. It has n bits, n slots, and I need to pick k of them to hold ones. So I need to pick k items from a set of n possible items, and that means that my answer for how many strings there are is our friend the binomial coefficient, n choose k. So this means that the probability mass function for x evaluated at k, the probability that we observe exactly k successes in these n Bernoulli trials, or k1s in this random string. So that's equal to the sum over all possible strings s containing k1s and n minus k zeros of the probability of that string. And we already figured out, hey, all of these strings have the same probability. It's right there. Every string in that set has the same probability. And we know how many of them there are. There's n choose k. So this sum is going to have n choose k identical terms, all with probability p raised to the k, n minus p raised to the n minus k. And so this is our probability mass function for this random variable. So this random variable has a special name. This is also very important, the number of successes in a series of independent trials. This is called a binomial random variable. And what we have just derived here is the PMF of a binomial random variable. So, Bernoulli random variables describe coin flips, a single coin flip with some bias in the coin described by a probability p. Binomial random variables describe the aggregate result of many coin flips. If I flip a coin many times, n times, that coin has some bias equal to p. What's the probability of observing some specific number k of successes or heads in all those trials? It takes a little work to get there, but we can derive this binomial distribution, binomial probability mass function named after our friend the binomial coefficient sitting right here.